Okay, we can bypass the microwave state preparation stage still to do AI. So for the normal case, we do melt, we do subdoppler cooling, then we get the atom, let's say 10 to the power of 8 atoms with 5 microkelvin atomic clock. And then we do optical pumping. We pump all the atoms in the Fe2 state by shining a ray pump light. That is from 1 to 2 prime on resonant light. And then we do microwave. We transfer 2 0 state to 1 0 state. And then we do blow away. We blow the plus minus 1 to plus minus 2 state away. So at this stage, the system only left with these atoms. And then we do AI. So it's gonna couple these two states by shining the Raman pulse sequence. That detection. This is how we do AI conventionally. Since now we don't have microwave, then what we should do is still melt, sub-D. Then we do optical pumping. We use 2 to the 3 prime light, because after sub-D, the atoms are populated in all of this state. F equal to 1, F equal to 2. This is minus 2, minus 1, 0, plus 1, plus 2. The atoms are everywhere here. Most of the atoms are in the F equal to 2 state. Very few in F equal to 1. So what we can do is we shine the 2 to the 2 prime, 2 to the 2 prime light. So the atoms will be populated to here, here, and here, evenly. Let's say 1/3, 1/3, 1/3. Okay, start from this. We can directly do AI, use these atoms. What we need to do is give a huge bias speed field. You know, when we give the bias speed field, the atom gonna do the Riemann splitting. Let's say this is the middle peak co-propagate middle peak, and this is the sidebands when we shine the Raman beam. So this is 1 1 2 2 1 1 0 2 2 0 1 minus 1 2 2 minus 1. This, let's say, is a co-propagate. And we also have the counter-propagate light. We have the counter-propagate moving up, counter-propagate moving down. This is the counter-propagate. 1 0 to 2 0. 1 minus 1 to 2 minus 1. 1 plus 1 to 2 plus 1. And the space between this is the same, because this delta prime equal to delta y, because this is defined by the Riemann splitting. This is defined by the bias speed field. Okay, what we really care about is this peak. This is moving downwards. Let's say K factor moving downwards. K vector moving upwards. We also have another step. Right? This -1 to -1, 0 to 0, and 1 to 1. right? And the space between this delta is defined by the velocity. Yeah, how far it moved. Because this is Doppler sensitive, this is Doppler insensitive. If your atom moves very fast, then you need to kill your Raman beam to compensate it, right? So that is why it's moved away from the central peak.
Okay.
Okay. And then what we can do is, this is how we do it in our setup in Boltzmann. What we can do in Dirac, because you don't have the microwave, what you can do is apply a huge magnetic field. Let's say I remove this part. This is still the frequency, the relative frequency between the two Raman beams, and the middle peak is still there. But since the B field is so huge, this is 1, 0 to 2, 0, 1, 1 to 2, 1, 1 minus 1 to 2 minus 1. And we move we let the atom drop such the counterpropagate. This is the co-propagate. PL. This is the counter propagate. This is also counter propagate. So we can let the counter propagate light still within this range, within this range. Let's say we drop it for overall 10 milliseconds. 10 milliseconds, we drop it. So this is 1, 0 to 2, 0 co-propagate, and co-propagate with plus k. And here symmetrically you have 1, 0 to 2, 0 minus k, right? And you start your experiment from, let's say, 5 milliseconds here, 5 milliseconds, all the way to 10 milliseconds. So your T is 2.5 milliseconds, for example. Okay? Right? And where is your magnetic sensitive state in this case? It is also very far. It is, for this one, let's say the space is even, then I erase this peak for now. So this is 1, 0, 1 minus 1 to 2 minus 1 plus k. This is his. And this guy's peak is somewhere here. This is 1 plus 1 to 1 to 2 plus 1 minus k. But it won't touch each other, so you are safe. So in this range, you can work it nicely.
Okay.
They won't talk to each other. You won't have the peak overlap issue.
But the signal will be very weak, right?
Not really. Your signal will be 30% of the atoms participating in AI. That gives you, let's say, if you have 100% atoms and you have 20% contrast, for 30%, you have 6% contrast, right? And the 6% contrast sit on the 66% of the background atoms. Yes, it's gonna be like this. So what you have is probably these fringes, and this will be 70% something, and the contrast is 10%, for example. Yes, over here. But that doesn't stop you to test the AI at least.
Yeah,
maybe by that time You already received
Yes, yes.
microwave, then you can do.
He said you take 10 weeks to find a microwave. Yeah. He said you 10 weeks to do AI.
Yeah.
Your thing is low battery value.
Oh, low battery. Is this still recording?
Yes.
Nice.